Right, I've got two curves here. This green one, which is f of x equals 3, x minus 4 all squared plus 5. And that one, which is 3x squared minus 24x plus 53. And my point is that they are exactly the same. And they're exactly the same because they're the same quadratic. The bottom one, the red one, is written in something called standard form, and the top one is written in completed square form. Now, you need to know how to go from one to the other, and you can practice that. There's plenty of information on the slides, and I've got worksheets and stuff like that. It's just a process you need to be okay with doing. Sometimes you'll get a 2-mark question which will just give you a quadratic in standard form and ask you to write it in completed square form. So even though there are ways of avoiding completed square form in longer questions, there are some questions where it's not possible to avoid it, so you do need to know how to do it. Now, if you look at the standard form, this orangey one, you can see that from the information that you've got there, you've got a is 3 because it's in the form ax squared plus bx plus c, a is 3, b is minus 24 and c is 53. It's difficult to work out anything about the quadratic. You do know that the y-intercept is at 53. If we scrolled right up here, am I going to bother doing it? I am. You'd see that we actually have a y-intercept of 53. You can tell that from standard form, but you can't tell where the vertex is. At least you can't incredibly easily. From the other form, completed square, you can. Now, if you take the number b, which in this case is minus 4, and change its sign so that it's plus 4, and then you take the number c, which is 5, and don't change its sign, you get 4, 5, and you will see that the vertex of the curve is at 4, 5. Just have a quick look at that. So when you've got something in completed square form, you automatically know where the vertex is. This 3 here at the front makes no difference whatsoever. I can change what that is. So let's change it to 5. Now, my quadratic's changed shape a little bit, and you can see that it's not exactly the same as the one before because I've mucked around with it, but the vertex hasn't changed. So it doesn't matter what that, I'll put it back to 3, what that first number is, that's not going to change where the vertex is. So if you've got it in completed square form, you know immediately where the turning point is. And that's one of the main reasons for wanting to convert something to completed square form, because you can just kind of read off where the turning point is. Now, it is also true that if you look at this form, standard form, you can actually, if you have enough knowledge, read off the vertex from there. So let's remember that you've got A is 3 and B is minus 24 and C is 53. The turning point from this form is at minus B over 2A. So if you take minus B is 24 and you divide it by 2A, you'll get 4. That gives you the x coordinate of the turning point. So it gives you the line of symmetry. If you then take that value of x being 4 and put it into the function, you'll end up with 5, and that'll give you the turning point. So you can also work out the x coordinate of the turning point from standard form, but I think most people probably find it easier using the completed square form. Okay, so that's one important reason for deciding that you want to use the completed square form. We had this question before, which I've got in another video, where we wanted to first of all differentiate a position function here. So this function, let's see if I can, that function there is telling you for a given t where you are, where you're actually standing. We differentiate that to this function, which tells us for any t what your speed is, i.e. what your rate of change of position is with respect to time. And it was that function that we decided was a u-shaped quadratic like this, and we wanted to find where it was at its minimum, i.e. where its gradient was 0, and that's at the bottom. So we took the second derivative of this, which gives us the gradient function of the speed function, which is this, and then we set that to be equal to 0, i.e. where is the point at which the gradient is 0, solved for it and got t equals 3. And we said another way of doing it was to convert it to completed square form, as we did here, and then we can just read off. We take this one and change its sign, and take this one and don't change its sign, and that is the coordinate of the turning point here, 3, 6. Okay, so there were two different ways of doing this. We decided that we might take the second derivative and solve for 0 to find out the turning point, or complete it turn it into completed square form, and just read off the point. And of course, the point of the minimum shows us where the speed is minimum, because it's kind of the y coordinate, or in this case the v coordinate, because this is time t equals 3 and our speed then is 6. Okay, and so we can read it off here and just state the answer. Just to prove to you the thing about minus b over 2a, if we take minus b over 2a using this speed function here in standard form, not in completed square form, minus b is 18, 2a is 6. That gives us the t coordinate then of the turning point, and we're kind of at the same place. We can then put t back in. We're at this. We're at this point, having found the t, and then we can do this bit to find the 6. So either of those three ways is absolutely fine. If you do use this minus b over 2a thing to find the x coordinate of the turning point, you must write that down. You can't just conjure the answer like this. You would have to say something like x coordinate of turning point at minus b over 2a. Writing that, and you wouldn't have to write it in long form or anything more than that. Writing that would show that you know what you're doing, and that would be another way of finding the turning point. So all we wanted to find out was the bottom of this graph, and we have three different ways of doing it: differentiating, putting it in completed square form and kind of reading it off, or using this funny minus b over 2a thing, and then taking the time that we found and putting it back in to find the speed. Okay, now this is another case where you do need to use completed square form. You are being asked, so let's have a look at the question. You've got two functions f and g. One is f is a quadratic, and it tells us importantly x is greater than or equal to 1. So the domain of f is x is greater than or equal to 1. And it also gives us the function g, which is linear, i.e. it's not a quadratic, it's just a straight line. And it first of all asks us to find f of g of 2, and that's pretty straightforward. G of 2, so we would kind of work out g of 2 is we just put a 2 wherever we see the x in g, and that gives us 8. And then we've got to feed that into f. So now we do f of 8, and that's equal to 5 times 8 squared. 5 times 8 squared minus 10 lots of 8 plus 7, and you'd put that in your calculator, not doing what I'm about to do, which is doing it in my head. 564s are 320 minus 80 is what 240 plus 7 is 247. Okay, so that's the answer to part A. That's not really what we're concentrating on, but I thought I'd do it. B asks us to find the inverse of this quadratic in standard form. So standard forms where it's probably the most familiar form, ax squared plus bx plus c. What we want to do is kind of take this expression, I'm going to write it down, y equals, and I'm going to put y because the y is easier to play with than f of x. Y equals 5x squared minus 10x plus 7. What I want to do is rearrange this and end up with x equals something in terms of y, so some expression in terms of y. But there's no clean way of doing it from this kind of format. From standard form, you can't do it. You'll just end up with something that you can't work with. So the way that you must do it at this point is to rewrite the function in completed square form. Okay, so we'll do that now. We've got 5x squared minus 10x plus 7. It's this bit that we want to complete the square on. And the first thing we need to do is get x squared so that it has a positive coefficient of 1. That's important to do. So the way to do that is to divide it by 5. Luckily, minus 10x divides by 5 nicely as well. So we're going to take the 5 outside. That means on the inside we're going to have x squared minus 2x, and then we've still got plus 7. So it's now just this bit that we want to complete the square on, and that is going to give us 5. We're still multiplying by something, but the thing that to complete the square we're going to halve the second term. So I'm just going to make that a bit clearer. In brackets here, x minus 1 squared. That will give us x squared minus 2x, but then it'll give us plus 1 at the end, which is annoying. So we just take that off, minus 1, and everything's right there. All I'm now going to do is remove the outer set of brackets. 5x minus 1 squared. I've got to multiply this minus 1 by 5, and then outside the bracket I've got a plus 7. And just to simplify that, that gives me 5x minus 1 squared plus 2. And that's the same quadratic, but written in completed square form. At this point, I can actually sort of unpick this and get x on its own, which is what I want to do. So I'm going to start with y equals 5x minus 1 squared plus 2, and I'm just going to start undoing it until I get what I want. So first of all I'm going to take away 2, so I'm going to get y minus 2 equals 5x minus 1 squared. Then I'm going to divide by 5, so I'm going to get y minus 2 over 5 equals x minus 1 squared. Now I've got to take the square root, and I'm actually going to swap the x over this side, so x minus 1 equals the square root of y minus 2 over 5, but it could have been the positive square root or the negative square root. Okay, if I squared those, I'd get back to y minus 2 over 5, whether it was positive or negative. And now I can just add 1. So going up here, that gives me x equals 1 plus or minus the square root of y minus 2 over 5. And I'm going to just pause here and look at this fact. It tells me that the domain of f is x is greater than or equal to 1. That means the range of the inverse, the range of this is going to be have to be x is greater than or equal to 1. So that's an important fact. If the range of a function is x greater than or equal to 1, then, if the domain of a function is x greater than or equal to 1, that means the things that you can put in it, then the range of the inverse will be the same. So that means this thing here always has to give me answers that are greater than or equal to 1. And I can see that I've got a 1 and I'm either adding something or subtracting something to it, but I'm not interested in ever subtracting anything because that won't give me things that are greater than 1. So in fact, I'm going to reject the minus sign and just call this 1 plus the square root of y minus 2 over 5. And I've got one other thing to do, which is kind of just swap x and y for the correct notation here. So instead of saying x, I put f to the minus 1 of x. And in here, 1 plus, because I don't want the negative, instead of putting y, I put x. That's just a sort of changing notation thing. No maths is happening there. That's just me swapping some stuff out. And this is now the inverse function. I couldn't have done that starting with this completed square. This standard form. You can't do it. So if you are ever asked, the short point here is if you were ever asked to find the inverse of a quadratic that is in standard form, first of all, go to completed square form and then proceed as normal by kind of unpicking it through reverse operations. Don't forget this plus or minus bit here. That's important. Do be careful to look to see if the domain is restricted, and indeed it must be restricted, otherwise you can't end up with a function. If it's restricted, look very carefully. They've given us a kind thing here. We can obviously see that one of these versions is going to end up being greater than 1 and one of them is not. So then we reject the correct one. Then we've just got this last bit of sort of relabeling to go there. And this is your final answer. Okay, so it's important to know that's a good time to decide to use completed square. The other time is when you want to know what the vertex of a quadratic is, when you want to just kind of read it off.